Hi there. Today we're going to talk about the RLC series circuit. This is a continuation of the series I'm doing looking at series circuit calculations, starting off with the RL circuit. I moved on to RC, and now we're into the RLC. So what does RLC stand for? Well, it stands for resistive, inductive, and capacitive circuits. We've got values of resistance, 60 ohms in this particular circuit. I've got 85.7 ohms of inductive reactance, and down there on the end, I've got 75 ohms of capacitive reactance. I've got everything inputted here in the chart, and I'm going to discuss and show you how to go about using a series of formulas, both using Ohm's law and trigonometry, to solve for all of these missing values. Looking at what we have to work with, I've got values of resistance, inductive reactance, and capacitive reactance, and it's going to be using a simple trigonometry formula to solve for the value of circuit impedance. Now, once I have circuit impedance, I'm going to be able to unlock the value of current, and then it'll be just a matter of going through the paces. So follow along. You'll need pen and paper, well, preferably a pencil, and a scientific calculator. So let's get started. Our first step is we're going to calculate the value of circuit impedance. Now, inductors and capacitors negate each other, and that's reflected here in this formula. You'll see that we're using a variation on the formula of trigonometry that we've used previously, but here we're actually subtracting the value of capacitive reactance from the inductive reactance. Whatever that remains is going to be a value of reactive power that we're going to be drawing from the circuit. So I'm going to plug in the values that we were given, and we'll just go through the exercise. "60 ohms of resistance squared plus 85.7 ohms subtracting 75 ohms of capacitive reactance, and then the square root." As a single operation in a calculator, remembering the PEDMAS rules, you should get 3714.49 square root, and the answer for impedance is going to be 60.95 ohms. So there's our impedance. I'm going to go ahead and input it down on the chart, and at this point, now that I have impedance, I'm going to use an Ohm's law formula to calculate the value of circuit current. Now that I've got impedance written down at 60.95 ohms, what I'm going to do is I'm going to use Ohm's law, and we're going to calculate the value of current draw for the entire circuit. So I'm going to meet you down there. Now we're going to move on to the second step, which is namely calculating the value of current that is going to be drawn for the entire circuit. We're going to take the value of the applied voltage, and we're going to divide it by the value of impedance. I'll just input our values. "118 volts, and it's going to be divided by the 60.95 ohms of impedance. As a result, our current is going to be 1.94 amperes, or amps for short. Now that I've done this, I'm going to input it in the chart, but this is going to give me the current draw for the entire circuit. Now that I've calculated the total amount of current for the circuit, 1.94 amperes, this being a series circuit, I can take this value and I can put it in each of the branches, because series circuit, the current is going to be the same at any point in the circuit. Once you've got the current as a value known, it's just a matter of using the current and the individual value of resistance, inductive reactance, or capacitive reactance, and we could solve for the voltage drop. So 1.94, very easily, we'll just input that right across. Now, because I've got the current already set up, I am going to go and solve for all the missing values in each of my components first before I go and tackle the entire circuit. Moving forward, step number 3, calculating the voltage drop across the resistor. We're going to be using, again, simple Ohm's law. We're going to take the value of the current that we just calculated, and we're going to multiply it by the value or given value of resistance. In this case, it was 60 ohms. So let's input that. 1.94 amperes multiplied by the 60 ohms of resistance, and as a result, the voltage drop across that resistor, or E sub R, is going to be 116.4 volts. Of course, rounded to 2 decimal places. Now that I have this and it's inputted in my calculator, I'm going to proceed automatically to step number 4, and I'm going to calculate the power, or the value of true power, that this resistor is going to draw from the power supply. Now, we're using, again, an Ohm's law formula where P is equal to the value of the induced voltage, or the voltage drop across the resistor, and multiplied by the current that the resistor is drawing. We can add our values, which will be 116.4 volts multiplied by the current, 1.94 amperes, and the result is going to be, for power, you have to bend down a little bit here, 225.82 watts of power. Now, this concludes all of the missing values across the resistive component in my series circuit. So I'm going to go and put this into the chart, and then we're going to move down and we'll start solving for the other missing values in the different components that still make up our circuit. We've got all of the values solved for our resistive component. Now I'm going to move on to the inductive components. We see that I'm missing, for the voltage drop across the inductor, the amount of reactive power that the inductor is consuming, as well as the value of inductance. So I'm going to get all 3 of these done consecutively, and before I come back and input this on the board. Step 5, calculating the voltage drop across the inductor. Ohm's law formula, the voltage drop is going to be equal to the amount of current draw multiplied by the value of inductive reactance. So let's put in our values. 1.94 amperes multiplied by 85.7 ohms. The result should be our voltage drop is equal to 166.2 0.26 volts. Now, some people are going to be shocked because 166 volts is higher than the applied voltage of 118. How can this be? Well, it is interesting because the math is correct, that you are going to generate higher voltage than that, pardon me, I'm tongue-tied, but you are going to generate higher voltages, but the math is correct. And in real life, it does happen. And I will be showing that in another video where we're going to be looking at the amplitude of the voltage drops across and see if they actually do coincide. And this is standard. Now, having said that, let's move on to step 6, which will be to calculate the amount of reactive power, or VARs sub L, that the inductors are going to absorb or consume. Again, we're using an Ohm's law formula where VARs sub L is equal to the amount of voltage drop across the inductor multiplied by the current of the circuit. In this case, 166.26 volts multiplied by the 1.94 amperes. So VARs L should equal 322.54 volt amps reactive. Now I'm going to proceed and I'm going to go and chart this. Oh, and you know what I forgot to do? Step 7. We've got to calculate the value of inductance. Well, I'll erase this and we'll do the value of inductance and then we'll chart it all together. I'm going to have to erase this. I'll be right back. This brings us to the last value we must calculate for this branch of the circuit. What we're going to do is calculate for the value of inductance. This formula, we're going to take the value of inductive reactance and we're going to divide it by the two given values in this formula, which is 2 times pi and the frequency, which happens to be 60 hertz here in North America. If you happen to type this into a calculator, you should get for an answer 377. And this is pretty much a stable value that you can input, but it only works if the frequency in your circuit is 60 hertz. It does not function if you've changed frequencies such as 50 hertz or 25 hertz, then you would actually have to input this in a longer format. So let's put in our numbers. So 85.7 ohms of inductive reactance divided by 377, and you're going to get a value of inductance of 0.227 henries. Okay, so we found the voltage drop, the amount of reactive power, and we wrapped it up with the value of inductance. So I'm going to head down and I'm going to record all this in the chart, and I'll be right back. Okay, we're done with the inductor. Last component, the capacitor. Follow me down. We're going to get that one done next. Step 8. Calculating the voltage drop across the capacitor. We're going to take the current drop of the circuit, which was 1.94 amps, and we're going to multiply that by the value of capacitive reactance. In this case, it was 75 ohms. So I'm just going to go ahead and put that down on the board. As a result, the voltage drop across the capacitor is going to be 145.5 volts. So you may have noticed a trend that the voltage drop across the inductor was quite high. If my memory serves me right, it was about 166 volts, and here we have 145 volts. Yet the applied voltage is 120. Have no fear. The math is correct. I didn't make a mistake. And I will be able to prove it, but when you're dealing with RLC circuits, there's a lot more going on. What it is that we have an exchange of energy going on. And I'm going to have to get in a little bit deeper into this. What we're dealing with is that when the voltage sine wave is continuously expanding, contracting, and reaching its peak, and then when it goes down, you actually have the magnetic flux inside of the inductor that is actually collapsing, and it has to go anywhere. Physics tells us that energy can't be destroyed, but what's happening is during that period of time that that magnetic field is collapsing, it is actually, the energy is flowing into the capacitor and it resides as an electrostatic charge. And what we're having is a game of ping pong, if you will. I think it's the best analogy I can come up with, where you've got energy that is seesawing backwards and forwards from the electrostatic charge that resides inside of a capacitor to the electromagnetic field of the inductor. And at different points in the sine wave, this is what we're seeing. This is one of the reasons why we're producing really high voltage drops in a series circuit. And I will be able to prove it. Now, getting back to our calculations, we're going to move on to step 9, and that's going to be calculating the amount of reactive power that the capacitor is generating. And yes, I said that correctly. Capacitors generate reactive power and inductors absorb it. So let's move on. So let's take the voltage drop that we've just calculated, and we're going to multiply that by the current draw, and that's going to give us the value of reactive power that our capacitor will be generating. So 145.5 volts multiplied by the 1.94 amperes, and that's going to give us for a result, let's see here, 282.27 volt amps reactive. Now, I've got one other thing to calculate, and that's going to be the value of capacitance. I'm going to erase this, and we're going to move on to step 10. Step 10, determining the value of capacitance for a capacitor. We're going to be using this familiar formula where it's the reciprocal, or 1 over 2 times pi times the frequency times the value of capacitor reactance. So let's write that out. 2 multiplied by the value of pi, 3.1416, multiplied by the frequency of 60 hertz, multiplied by the value of capacitor reactance, and then the reciprocal. There's a little bit of a shortcut in that I can just use 377, which is 2 times 3.1416 times 60 hertz, and multiply that by the 75 ohms, 1 over. Now, that being said, you're going to have for an answer 35.37 microfarads if you've done your calculations or if you've done your work accurately, pardon me. Now, this sums up everything for the capacitive branch, not branch, but the capacitor that is in our series circuit. I'm going to go and input all these values in the chart, and then we're going to start looking at the value of apparent power for the entire circuit. Well, now that I've got that done, it's time to move on to solving for the total amount of apparent power that my circuit is going to be consuming from the power supply. So what we're going to do is we're going to use a trig formula, which is basically a variation off of formulas we've used previously. And then we'll go on to power factor or circuit efficiency, and then we're going to finish up with angle theta. So let's just keep trucking. Calculating the amount of apparent power that the circuit requires. This is a really interesting formula because it reflects a couple fundamental items. The fact that capacitors oppose a change of voltage and inductors oppose a change of current, and they basically negate one another. And that's reflected here in this formula. You'll see that the amount of power that an inductor absorbs is actually going to be given from a capacitor. The capacitors generate reactive power, inductors absorb it. And if we can closely match the amount of capacitance to the amount of inductance, the overall effect is I'm going to improve the power factor of my circuit, meaning my circuit is going to be more efficient. That's the ultimate goal that we're working towards. Now, enough about that. Let's proceed to start inputting our values. So if we have, 60 ohms is the value of resistance. The value of power is 225.82. Whew. That could have been a catastrophe. Now, head mass, we open up the brackets, 322.54 vars L. We're going to subtract the 282.27 vars volt amps capacitive squared, and it's a long formula, so I'm going to use a ruler here. Now, putting these values into a calculator, the result would be 52616.3453. Now, obviously, we still have the operation of doing square root, and that is going to take us to a final answer of 229.38 VA or volt amps. Now, I'm going to input that into my chart, and then we're going to start working on finding the value of power factor, and we're going to finish up with angle theta. Okay, VA taken care of. On to power factor next. We're going to work out the efficiency of the circuit, and if you've been looking at any of my previous videos, I tend to work from the formula of power. Reason being, it does not matter whether or not the circuit is series, parallel, or even a combination circuit. Working from power is a very simple and straightforward, as opposed to trying to work with values of impedance, resistance, or in this case with the series circuit, the voltage drops. Yes, those formulas can be used and they are accurate, but it's easy to forget. And that's one of the reasons why I always advocated, let's work with power. As time goes on, and I will be showing people how to solve much more complicated circuits, and what you're going to see is that working from power is much, much easier. So let's just proceed. So the power that we calculated was 225.82 ohms, and our VA that we just finished calculating was 229.38 ohms. I can tell you right now, because there's such a small difference in between these two values, that the value of power factor is going to be extremely high for this circuit. Now, punching this into a calculator, the result is going to be 0.984469401. Now, this is going to be expressed as a percentage, but how I do it is I just move the decimal 2 places to the right, and I will just proceed to write out power factor is 98.4, so we're going to round up to 45%. That's extremely high. Power factor, the upper limit is 100%, but this is what would be considered really good power factor. You would not be paying an awful lot of extra money, or in other words, there's no wasted energy in this type of a circuit. Now, last thing to calculate, angle theta. So cosine of angle theta is equal to the value of the power factor, but we're going to be using the decimals. In this case, we're also going to have to isolate for the value of angle theta. So angle theta is going to be equal to the power factor and then negative cosine. Now, this value should be still located in the memory of your calculator, and it's just a matter of pushing negative cosine, and you would actually, in one operation, get the answer for angle theta. And as a result, angle theta, if we put 0.9845, is going to give me 10.11 degrees. What's interesting is that when you have high power factor, that the angle theta, or the phase angle difference between the voltage and the current, is going to be very minimal. It could be said that power factor and the phase angle difference, or angle theta, are inversely proportional to one another. The higher the power factor, the less the phase angle difference, which kind of tracks with what we see with a purely resistive circuit where we have 0 phase angle difference. So I'm going to wrap this up. I'm going to enter these last values in the chart, and then we're going to proceed to talking about the type of phase angle difference. And I'm going to expand on that in just a few minutes. Now, with this segment, we have finished calculating all of the missing values in our circuit. One of the things we need to understand, though, is with this power factor, and more importantly, angle theta. Because I'm working with a circuit that has both inductive and capacitive components, and that we've seen through this process, mathematically, one will negate the other. And in this case, I have to figure out this angle theta is the phase angle, or the voltage in current waveform. Is the voltage leading the current, or is voltage lagging behind the current? Right now, I know mathematically that I have a 10.11 degree of difference, but I don't know at this point which way is this going. And same thing with the power factor. There is a concept that power factor could either be leading or lagging. And I'm going to expand upon this, but I've got to erase a couple things here, and I'm going to get a tighter close-up here. Here in this circuit, I've got a value of reactive power across the capacitor and a value of reactive power across the inductor. And we can see numerically they're not the same. Capacitors generate reactive power, inductors absorb it. In this case, I've got 282.27 volt amps reactive, and that's going to negate that portion, of what is volt amps inductive. So this, basically, if I subtract 282.27, I'm going to have 40.27 volt amps. But these are going to be volt amps reactive inductive because I've totally canceled the amount of reactive power that the capacitor was generating. This means then that I'm going to have the voltage leading the current, because this is a series circuit, but the voltage will be leading the current by 10.11 degrees. Now, in a textbook, if you're reading this, if you've got more reactive power that is coming from an inductor, that gives you a lagging power factor. So what I'm going to have to do is, on the chart, I'm going to be writing out that I have a lagging power factor, and we're going to display this when we start talking about the voltage and current relationships. Here we have what represents an oscilloscope display and across the resistive component in our series circuit. Being a series circuit, the current is a stationary waveform and the voltage waveform changes in relation to the stationary current. As such, what we have is a zero phase angle difference. So because of the fact that we don't see any changes in the phase angle between the voltage drop waveform and that of the current, we have to, or we can say, that they're in phase with one another. So at the 0 point, the voltage waveform is actually going to travel in the exact same path. There's just going to be a slight difference in the amplitude of the voltage waveform to the as compared to the current waveform, but they both rise in unison, peak in unison, and collapse in unison, and they go into the negative alternation in unison and continue in this same relationship all throughout the cycle or the waveforms. Now, we're also going to spell that out, and more importantly, if you're using the same color of writing implement, let's say a pencil, you should be identifying that waveform. And we're going to identify it by its algebraic expression, E, which is what we would use in a formula to identify for voltage. And we are going to spell out that voltage and current are in phase, and that angle theta is equal to 0 degrees across the resistor. Now, I'm going to move on to the inductive component. Dealing with our inductive component, it is said that inductors oppose a change of current, and as a result, that the voltage ends up leading the current in a series circuit by 90 degrees. Why does the voltage lead? It's because of the fact that the current is the same at any point in the circuit. It becomes a stationary waveform that all others move in relation to. As such, here's our 90 degrees. There's 180, 270, and 360. And the voltage is leading. So that means then that the waveform is going to start up here. Now, I'm exaggerating the amplitude because of the fact we are on film and I want to really capture this. So we're going to start up here. We're going to peak when the current is at a 0 value. Well, that's when the voltage waveform will peak, and then it'll collapse and cross over at 90 degrees of phase angle difference, and continue on the same trend. I'm going to identify it, and I'm going to spell this out and mention that voltage leads the current by 90 degrees in a series circuit. Okay, we've got that one wrapped up. Now let's do the voltage and current relationship for the capacitor. Now, capacitors, they oppose a change of voltage, and as a result, in the textbook, you'll see that the current leads the voltage. But in a situation where the current can't move, then we'll have to apply the reverse logic and say that the voltage is going to lag behind the current by 90 degrees. And so this is basically going to be the mirror image of the voltage waveform that we just drew for the inductor. Where it was leading, it now lags, and we're going to draw it down here. It's going to cross at 90, peak up here when the current waveform is at 0, and then continue on the same trend. So if I start from here, peak, come down at 90 degrees, I'm maintaining that phase angle difference of 90 degrees and continue on. Identifying my waveform, and we're going to mention that voltage lags the current by 90 degrees in a series circuit. Okay, last thing to do, we're going to draw the voltage and current relationship for the entire circuit, which is going to be based off of angle theta. So now we come to the end, charting the voltage and current relationship for the entire circuit, and it is represented by Z or impedance. Now, we figured that angle theta, through our calculations, angle theta was equal to 10.11 degrees, and that we had a lagging power factor indicating that the voltage was going to lead the current. So if my current is starting at 0, then my voltage is actually going to be slightly leading. And I've taken the liberty off camera of breaking things down. This is basically 90 degrees. Here is 45. Half of that will be 22.5, and at 10.11, I'm close to being here. So that means then that I've measured off an equal distance, and if I start my sine wave here, it's going to peak right about here, about 3/4 of an inch off, if I'm looking at this correctly. So I'm going to start up here, peak, collapse, it's going to come 3/4 of an inch short here, peak, collapse, and follow the same trend. I'm going to identify it because the phase angle difference is right basically here. If I drew the straight line, the voltage is ahead of the current. Not by much, but it's there if I follow this line all the way up. So this is what is meant by that leading power factor. Now, we're also going to write out that voltage leads the current by angle theta, and in this case it was equal to 10.11 degrees in a series circuit. Now, it's important to note that it was only based on the fact that if we had to establish whether or not that power factor was leading or lagging, that gave us where should we base this. If it had been leading, then what would have happened is the current was going to be ahead of the voltage, and the voltage would have actually started here, and I would have actually drawn it 10 degrees on this side of the current waveform. But because my voltage is actually leading the stationary current, it's actually 10 degrees on the left. I hope you found this informative, and if there's still any doubts in your mind about the validity of what we've done here, please check out my video where I'm actually building this circuit and we're measuring it in real time with an oscilloscope. Until then, please stay safe and like and subscribe. Bye now.